Let's talk about the periodic table, the ultimate map of the universe's building blocks. It's more than just a chart, it's a key to understanding the very fabric of everything we see, touch, and even breathe. This table is a masterpiece of science, carefully organized to reveal hidden patterns and relationships among the elements. You've seen it in classrooms, a grid of colorful boxes, each representing a unique element. But have you ever wondered why it's arranged that way? Each row and column tells a story about how elements behave, how they interact, and why they matter in our daily lives. But it's not just a poster, it's a guide to everything around us, from the air we breathe to the devices we use, the water you drink, the metal in your phone, even the oxygen in your lungs. All are made of elements found on this table. It's a silent companion, shaping our world in ways we often overlook. Think of it like a Lego set. The table shows us all the different bricks that make up matter. Just as you can build endless creations with Lego, the elements combine in countless ways to form everything in the universe, from simple molecules to complex living things. And here's the twist, the table isn't finished. There are still blank spaces, waiting to be filled by new discoveries. The periodic table is a living document, constantly evolving as science advances. Scientists are still discovering and creating new elements. In high-tech labs around the world, researchers push the boundaries of what's possible, searching for elements that nature never made. This journey takes us from ancient discoveries, when early chemists first isolated elements like gold and sulfur, to today's cutting-edge labs, where researchers use powerful tools and creative thinking to unlock new secrets of the universe. The search for new elements is a high-stakes adventure, using giant machines and incredible precision. Particle accelerators smash atoms together at nearly the speed of light, recreating conditions found only in stars or the early universe. Scientists collide atomic nuclei, hoping to create something brand new, revealing deep truths about matter itself. Each successful experiment adds a new piece to the puzzle, expanding our understanding of what the universe is made of. Like explorers mapping new worlds, today's scientists chart the far reaches of the periodic table, uncovering super-heavy elements that exist for mere moments before vanishing. These discoveries challenge our ideas about stability and the limits of matter. So buckle up, we're diving into the secret science behind the periodic table. Get ready to see how this iconic chart continues to shape our understanding of the universe, one element at a time. So what is an element? It's a question that sits at the very heart of chemistry and the study of matter itself. When we talk about elements, we're talking about the fundamental building blocks that make up everything in the universe, from the air we breathe to the stars in the sky. An element is a pure substance that can't be broken down into anything simpler by chemical means. No matter what you do, heat it, freeze it, mix it with other chemicals, an element remains itself. It's the most basic form of matter you can have. For example, gold is always gold, no matter where you find it or how you process it. Oxygen is always oxygen, whether it's in the air or in water. These substances are made up of only one kind of atom, and that's what makes them elements. Each element is defined by its atoms, and every atom of a given element is essentially identical in its core structure. But what really sets one element apart from another? The secret lies deep inside the atom, in its nucleus. Specifically, it's the number of protons packed into the nucleus that makes all the difference. This number is called the atomic number, and it acts like an atom's unique fingerprint. Hydrogen, the simplest element, has just one proton. Helium has two. Carbon, which forms the backbone of life, has 6. Each element has its own special number. If you change the number of protons in an atom's nucleus, you don't just get a different version of the same element, you create an entirely new element. That's how fundamental the atomic number is. The periodic table is a grand map, organized by atomic number. It starts with hydrogen, the lightest element, and moves up, one proton at a time, revealing a beautiful order to the elements. Elements in the same column or group share similar properties. Take the noble gases, for example. They're famously unreactive, barely interacting with anything else, and that's because of their unique electron arrangements. The atomic number doesn't just determine the number of protons, it also tells us how many electrons an atom has. These electrons are what control how elements bond, react, and interact with each other, shaping the chemistry of our world. When scientists discover a new element, they're not just finding something new, they're actually creating an atom with a never-before-seen number of protons. This is often done in powerful particle accelerators, where atoms are smashed together at incredible speeds. Proving you've made an atom with, say, 119 protons is a huge scientific achievement. It means you've pushed the boundaries of what's possible, adding a new piece to the puzzle of the universe. The periodic table isn't just a list of elements, it's a brilliant system that reveals deep patterns in chemistry and physics. It helps us predict how elements will behave, and even guides us in searching for new ones. Understanding atomic number is the key to expanding our map of matter. It's the foundation for everything we know about the elements and their relationships. Every new element discovered is like opening a new chapter in our understanding of the universe. Each one tells us something new about the forces and rules that shape reality. The hunt for new elements is about more than just filling in blanks. It's about pushing the boundaries of human knowledge and exploring the very limits of what's possible in science. In the end, the search for new elements is the ultimate proof that we're still exploring the unknown, always reaching further to understand the universe and our place within it. The periodic table is a mix of natural and human-made elements. The first 92 elements, from hydrogen to uranium, are found on Earth, some common, some rare. These elements were forged in stars and supernovae, making us all quite literally stardust. But elements beyond uranium, called transuranic elements, don't exist in nature. They're made in labs. These super-heavy elements are so unstable they decay almost instantly after creation. Starting with neptunium, every new element has been a triumph of nuclear science. Scientists smash atoms together to briefly create new, heavier nuclei. This is the modern era of element discovery, a high-tech quest to build the universe's missing pieces. Each new element is a fleeting glimpse into the unknown. The periodic table is still growing thanks to human ingenuity. The story of element discovery stretches back thousands of years, long before the word element even existed. Ancient civilizations were already familiar with naturally occurring metals like gold and silver, which they prized for their beauty and rarity. These metals were easy to find in their pure form, and people used them for coins, jewelry, and decoration, marveling at their luster and resistance to tarnish. Iron, copper, and a handful of other metals were also known in antiquity, even though people didn't yet understand what made them unique. Early blacksmiths learned to extract and shape these metals, forging tools and weapons that changed the course of human history. Yet the true nature of these substances remained a mystery. In the Middle Ages, alchemists, driven by dreams of turning base metals into gold, experimented endlessly. While their main goal eluded them, their curiosity led to the development of new laboratory techniques and the accidental discovery of elements like phosphorus and arsenic. These early scientists laid the groundwork for modern chemistry, even if they didn't realize it at the time. The 18th and 19th centuries marked a turning point. Chemists, such as Antoine Lavoisier, began to systematically study substances, carefully weighing and analyzing them in the lab. Lavoisier helped define what an element truly was, while others like Sir Humphrey Davy used electricity to isolate new elements, including gases like oxygen and hydrogen. Their discoveries revealed that air and water were not elements themselves, but mixtures of simpler substances. The real breakthrough came in 1869 when Russian chemist Dmitry Mendeleev organized the known elements by atomic mass and chemical properties, creating the very first periodic table. This table was more than a list, it was a powerful tool for predicting the existence of elements that hadn't yet been discovered. Mendeleev boldly left gaps in his table, predicting that future scientists would find elements to fill them. Remarkably, his predictions were soon proven correct as new elements were discovered that fit perfectly into the empty spaces he had left. The 20th century brought even more dramatic advances. Scientists uncovered the structure of the atom, discovered the atomic nucleus, and revealed the phenomenon of radioactivity. These breakthroughs allowed researchers like Marie Curie to isolate new radioactive elements and even create artificial ones in the lab. With the invention of particle accelerators, scientists could smash atoms together to create elements that had never existed on Earth before, such as neptunium. Soon after, they synthesized plutonium, kicking off an international race to discover and create super-heavy elements at the edge of the periodic table. Each new discovery filled in another square on the periodic table, expanding our understanding of matter and the building blocks of the universe. Over time, the periodic table has become a living document, constantly updated and reshaped by centuries of scientific curiosity, innovation, and collaboration. And even today, the race to discover new elements continues. as scientists push the boundaries of what's possible and deepen our understanding of the universe's fundamental ingredients. Making a new element isn't as simple as mixing chemicals, it's nuclear fusion. Atomic nuclei repel each other, so scientists use particle accelerators to smash them together at incredible speeds. A beam of lighter nuclei like calcium is fired at a heavier target, such as berkelium. Out of billions of collisions, only a rare few result in fusion, creating a super-heavy nucleus. For example, fusing calcium-48 and berkelium-249 creates tennessine, element 117. The new nucleus is unstable and quickly spits out neutrons, then decays into lighter elements. Scientists can't see the new element directly, they detect its unique decay signature. This decay chain is the evidence that a new element was born. Each successful fusion is a scientific triumph, even if the new atom lasts only milliseconds. The process is painstaking, but it's how we expand the periodic table. Every new element is a victory for human curiosity and technology. Creating new elements is one of science's toughest challenges. The target materials are rare, radioactive, and hard to produce, sometimes taking years to make just a few milligrams. Even with perfect ingredients, the odds of success are tiny. Maybe 1 in a quintillion collisions works. Scientists run accelerators for weeks, hoping to create a single atom. When they think they've succeeded, they must detect the atom's decay products and match them to predictions. One lab's result isn't enough. Another lab must independently confirm the discovery. This process can take years and involves international teams. Only after rigorous verification does a new element earn its place on the table. It's a global effort, driven by patience and precision. Once a new element is confirmed, it's time to name it. The International Union of Pure and Applied Chemistry, IUPAC, oversees the process, following strict rules. Discoverers propose a name, often honoring a scientist, place, or property. Examples include Einsteinium, curium, and tennessine. Before a name is official, the element gets a placeholder name based on its atomic number. After public review and IUPAC approval, the name is added to the periodic table. Naming a new element is the final step in making it part of human knowledge. Why go to all this trouble for atoms that vanish in a flash? Curiosity drives us, but there's more. Pushing the periodic table tests our understanding of physics and chemistry. In the super-heavy realm, the rules get weird. Relativity comes into play and new behaviors emerge. Scientists are searching for the island of stability, a region where super-heavy elements might last much longer. If found, these elements could have unique properties and real-world uses. The pursuit drives innovation in technology and medicine, from better accelerators to new cancer treatments. Even if we never reach the island, the journey itself advances science. The quest for new elements benefits us all. The periodic table story isn't over. The heaviest element so far is oganesson, number 118, but scientists are racing to create 119, 120, and beyond. This will start a new row and push the limits of technology and creativity. Labs worldwide are upgrading accelerators and inventing new methods to reach these elusive elements. The goal is to make enough atoms to study their properties and search for the island of stability. Every new discovery is a step into the unknown, guided by international collaboration. The periodic table is a living document, always evolving. Next time you see it, remember, there are still blank spaces waiting to be filled. The adventure continues and the search is on. Who knows what we'll discover next?